So what I'm going to be talking about today is the Bay of Bengal is a very strong region of strong air coupling in terms of SST and wind. But I'm going to be looking at the different aspects of air coupling where the momentum is strongly exchanged between ocean and atmosphere through the wind stress. And Bay of Bengal has a very strong surface current and surface winds, which is largely steady at basin scales, but the ocean's variability is incredibly strong. Then how does oceanic variability in terms of surface current can influence the surface stress, and how the surface stress can influence back to the surface oceanic circulation? So this is a working collaboration with many people, and I also like to thank Sudeep Jana at MIT and Amala. So this is animation from my model. This is 5 kilometer coupled Wolf-Rams models, and I'm going to be looking only oceanic process today. Atmospheric response is ongoing study. What I'm showing you here is the vorticity divided by F. So this is Rossby number in the two different simulations. And the only difference between these two simulations is the way the wind stress is parameterized in the model. So as you can see, there's a clear already difference in the stress formulation where conventionally we ignore the surface current in the stress formulation, thinking the ocean current is very small compared to atmospheric wind, so we can ignore it. But that's not the case for the oceanic mesoscale or energetic surface boundary currents, and that's increasingly well known that this relative wind effect, surface current, surface wind, relative surface current is increasingly important as you go to smaller spatial scales, and this influences eddy windwork, therefore eddy kinetic energy, and eddy-driven Ekman convergence, therefore stratification in the upper ocean. So difference between these two, large-scale structure, especially in the first month of simulation, remains similar. But then you can see there's a lot of some difference in these two simulations in terms of magnitude of the relative vorticity. So you can see that generally is much weaker compared to this. This very strong region of a Rossby number reaching number one is basically suggesting that this is a highly unbalanced flow. But then there's a large area of negative vorticity in this simulation, indicating that these are the large mesoscale eddies in the anticyclonic eddies. So you can see that magnitude is very different between the simulation. So you can look at the histogram to confirm this initial impression between this simulation is that this is a histogram between two different simulations. The red means the control simulation, blue is the run without the surface current. And you can see that as a function of Rossby number, so plus 1 and minus 1, you can see that the differences immediately pop up that in terms of heaviness of the tail, that the high Rossby number regime is much reduced in the simulation where you include the surface current. So this black curve shows this the difference in the histogram. So in terms of percentage difference, so you can see that it's all negative, meaning that relative vorticity is much smaller, becomes reduced when you include the surface current. So that means the flow seems to be stabilized. But the stabilization of this flow is happened to be much stronger in certain dynamic regime of Rossby number between 1 and minus 1 and minus half. So these are the range of similar to mesoscale variability and retouching the submesoscale regions. So in this kind of regime, this relative wind effect appears to be highly effective in terms of stabilizing the flow and in this area of especially the anticyclonic regime of the Bay of Bengal. So I'm going to be talking about more about the scale dependence of this of momentum coupling, and also this general damping of the eddy kinetic there's a flow field by this momentum coupling effect. So this is climatological eddy kinetic energy from the model. So this is control simulation, and this is a run without the surface current in the stress formulation. You can see already very large difference in eddy kinetic energy. This is about factor 2 difference in eddy kinetic energy, and this is very large compared to the other basins where we've seen this this effect turns out to be about anywhere between 20 to 50% damping of the kinetic energy. Bay of Bengal is the area where this damping effect is largest in the I've ever seen. It's about 100%. And this is a model, Aviso-based eddy kinetic energy. So there are some discrepancy between model and observation, but you can see that there's enhanced eddy kinetic energy along the western boundary of the basin. So this is EICC and the separation of the EICC. And model seems to capture some of the separation of the EICC, but doesn't capture much of the northern part of the EICC. But the difference is, again, is quite striking between the simulation. And again, this is the area of this very strong anticyclonic eddy. So this is a climatological sea surface height. You can see that there's a wind is southwesterly, and there's a very prominent anticyclonic eddy circulation here, south of the separated latitude of the EICC. So the scale dependence of the eddy kinetic energy damping by this relative wind effect can be seen in this wave number spectrum. So this is a eddy kinetic energy spectrum in terms of wavelength. So here's 1,000 kilometer, this is 10 kilometer, and two different simulations, control simulation and the run without the surface current. And the black is showing the percentage difference of this spectra. So you can see that between about 100 to 120 kilometer range, you can see that the eddy kinetic energy variance is reduced about 700, 800%. So this is a sort of the time spatial scale where this momentum coupling seems to be very, very important, effective in damping the kinetic energy of the ocean. And right panel shows the co-spectra, so of the surface current and surface stress. So this is sort of equivalent to the spectrum of the wind work, but I'm not doing the spectrum of the wind work because the spectrum of the variable that is a product of two different variables becomes very confusing. So instead, I'm trying to do doing this co-spectra of these two variables to get the insight of the spatial scale at which energy is imparted to the ocean by the wind. So again, I'm focusing on this black curve, which shows the difference in the wind work between two different experiments. You can see the general is all negative again, so which means that wind work is reduced also at all the wavelength band. But then it's particularly some wavelength band about 100 to 20 kilometer range is this damping of the wind work is most pronounced. And this 100 to 20 kilometer range is equivalent to first barochronic Rossby deformation radius. So this is really the major scale lattice that does work on the to try to reduce the wind work back to the ocean. And we already saw from the previous slide, this major scale eddies are highly prone, mostly anticyclonic eddy in the western boundary of the basin. Yeah, so yeah, I can show you a little more about this scale of this damping effect. So I think another consequence of this relative wind effect is stratification. It does affect the stratification in the Bay of Bengal. So this is mixed layer depth in the model. It's very shallow at the northern bay. It's about 5 meters, and they approach to about 20 meters, 30 meters in the southern bay, at the western bay. And this is a mixed layer depth difference. Most of the area is insignificant. Only area that pops up as a significant mixed layer depth difference is again this anticyclonic flow regime south of this EICC separation. And you can see about 5 meter reduction of the mixed layer depths, where climatological is about 20 meter or 30 meter depths. So it's significant reduction of the mixed layer depths. And I'm overlaying this black contour is the area of the mixed layer depth reduction of by 2 meters. So we're going to be focusing on this particular region. The question is, again, why mixed layer depths become shallower when you allow the surface current effect on the wind stress? So I'm calculating n square, average over top 200 meters. And you can see that there's a precisely where mixed layer depth shows, you see the increased stratification. So this is a very good case that suggests the mixed layer depth is shows because stratification increases. And this is the depth longitude cross section over this area. And then I'm overlaying a lot of lines. This can be very confusing, but these are the isopycners. So you can see that isopycners are generally move upward in the run where if you include surface current. And you can see the mixed depth also shows, thermocline depth also shows, but generally all the isopycners is moved upward in the experiment where with the surface current. You can see the stratification, color shading shows us change in stratification. So stratification increases below the mixed layer and decrease around the thermocline depth. So everything goes up, isopycners goes up, in that process increase the stratification in the bottom of the mixed layer. And then I also look at the shear square. So this is vertical shear of the horizontal current, and generally it's all reduced. So this is also consistent with the mixed layer depth shoaling. But in the area where we saw the mixed layer depth is more shoaled, within this black contour, you can see that generally is less reduced vertical shear. In fact, if you calculate the available turbulent kinetic energy over this region, there's enhanced wind stress or turbulent kinetic energy. And this is because of in this area, wind and surface current is opposite direction because anticyclonic flow regime acting with under the southwest westerly wind. So this enhanced turbulent kinetic energy cannot explain the mixed layer depth shoaling. So the only way the mixed layer depth shoals is because of the stratification increases. And the question becomes why stratification increases or why isopycners raised within the anticyclonic eddy in the presence of this current wind coupling. And I try to explain that in terms of the Ekman pumping velocity. So this is Ekman pumping velocity, full representation of it. First term is the current-induced Ekman pumping, where tau includes the surface current. And second term is the Ekman pumping just solely due to vorticity gradient of the flow field. So d zeta dy, d zeta dx. Third term is the small, it's a beta term. And the last term is I ignore in this study. This is SSD contribution to Ekman pumping, which might be important, but I'm not considering in this study. I'm comparing these two different terms, current-induced Ekman pumping and the vorticity gradient-induced Ekman pumping. And I'm showing you the change in this area. You can see that over mixed layer depth shoals, the area of the mixed layer depths becomes shallow. You can see that there's increased upward velocity by Ekman suction. And the change is about 100%, so about a factor of 2 increase in vertical velocity induced by Ekman divergence of this area. And this vorticity-induced Ekman pumping is very small and noisy and insignificant. So I can confidently say that most of this doming of the isopycner is due to the anticyclonic eddies interacting with the southwesterly wind that favor the upward motion. And this is depicted in this very idealized case. So this is again observed case where the anticyclonic eddy under steady southwesterly wind about 7 meters per second. And this is my Gaussian eddy, idealized anticyclonic eddy. The amplitude is about 25 centimeters from the observation. The radius about 200 kilometers. And then I impose a 7 meter per second surface wind. And the geostrophic velocity around this eddy is about 0.27 meters per second. And because, again, surface current affect the wind stress and Ekman pumping, so there's a current-induced Ekman pumping resulting from this interaction between wind stress and surface current, is that there's a monopole Ekman upwelling acting right on the center of the anticyclonic eddy. It's about 20 meters per day upward motion. And the vortice in this Ekman pumping produces dipole structure, northwest-southeast structure. And the total of this, sum of these two is a total Ekman pumping velocity induced by this major scale eddy is shifted a little bit westward, but then still very much acting to reduce this anticyclonic eddy amplitude by inducing upward doming of these isopycners. So this is summary. So I found the two types of response to relative wind effect in Bay of Bengal is that it reduced the eddy wind work and damps the eddy kinetic energy, especially in the south of the separate latitude of the EICC. And it also raised the isopycner within the anticyclonic eddies, and because the isopycners are domed, it increased the mixed layer stratification, and also in the process shallows the mixed layer depth. And I also note that the available turbulent kinetic energy actually increases. It's slightly offset, but this dominance is made by this isopycnal doming by Ekman pumping velocity. So this tells me the southwestern Bay of Bengal seems like a very interesting area in terms of momentum coupling between ocean and atmosphere.